Welcome to this lecture number 9 in the structural dynamics course, and we will switch from modal analysis from last week's lecture to the first lecture on damping of structures. It's the first lecture of 2, and in this lecture we will consider what we refer to as local dampers, and in particular viscous dampers acting on a structure. So we could have some kind of high-rise building, we could have a base down here, stories in between, and our problem may be that we could have some kind of chevron brace connecting a viscous damper between these two floors, number 1 and 2. So when the structure vibrates, we will have deformation of damper, and that will give us energy dissipation, and thus what we refer to as damping. Our problem is that this viscous damper here has a viscous coefficient C. If this tends to 0, the damper will have no effect. If the C value becomes too large, here indicated by an infinity sign, then the damper will simply lock this story between floors 1 and 2, and we will, in this case, have no damping. So both these limiting cases are associated with no damping, and the optimum is in between. So the question is, what is the optimal viscous parameter, and how much damping do we actually get from placing the viscous damper between these two floors? Would it be advantageous to put them one floor down or place them higher up in the building? And of course that depends on the vibration shape, that means the mode shape we would like to damp. Initially we will look at damping of cables, in particular stay cables on bridges. So our mathematical problem dates back to our solution of the cable in lecture number 5, and we will today simply place a local damper on the cable. But basically our problem is still solved by separation of variables, although it's somewhat more complicated, and the notation is also slightly different in this part of the course, so hopefully you'll be able to see the connection with lecture number 5. Once we have finalized the analysis of cables, we will go to the much more general case of local dampers on general flexible structures. So the idea is here actually to make a special type of modal analysis, what we refer to as a two-component subspace representation, based on two vibration shapes. So some of it actually refers to our analysis with mode shapes used in the previous 2 lectures, but of course it's a very particular case, so the representation also becomes somewhat more complicated. And the question is, of course, can we, based on this two-component subspace representation, reduce the system size down to a certain magnitude so that we can actually solve equations to find again the optimal viscous parameter and the maximum damping ratio that we get from this external damper placed on the structure. We will, in the analysis, consider dampers placed on a structure, but in reality and in most cases you can actually get a long way with simply looking at a single damper on a structure. The placement and sizing of multiple dampers we will omit in this lecture. It's in the slides and it's in the textbook if you at some point need it, and we will at the end have a look at what damping performance do we get out of this for this shear frame problem that I've illustrated very roughly on this first introductory slide. A large real-life problem considers the Sutong Bridge in China, where you can see, and this picture is of courtesy of Felix Weber from Maurer Söhne in Zurich, and you can see stay cables carrying the bridge deck and supported by major pylons, tall pylons. And what is of interest is, of course, that these cables can vibrate, in particular during wind and rain loading. The rain has a tendency to make a more aerodynamic profile on the cables, and thereby they become much more prone to in-plane vibrations. And those in-plane vibrations are taken care of by viscous dampers, connecting the cable to the bridge deck. And you can see they're placed on basically every cable. And the longest cables, those you can see up here, are half a kilometer long, and they're actually damped by so-called smart magnetorheological dampers that can adaptively change the properties so that they can be effective not only with respect to a single vibration mode, but actually to many modes, because they can shift their properties. On a somewhat smaller bridge, the Island Bridge in the Netherlands, you can actually see some of these, or one of these smart dampers, one of these magnetorheological dampers, and its classical connection with the bridge between bridge deck and stay cable shown over here. And what you see is that for this smart damper you can actually measure the deflection, and you feed that into a control system that adjusts the particle or the viscosity of this damper. So you can in real time change the viscosity of this damper. And that's a pretty good property. The drawback is that these dampers, at least the older versions, they didn't really last the entire lifetime of the bridge, so they need to be replaced. But you can see, because they're located here between the cable and the bridge deck, they're quite easily replaced by new models. So our problem is, or what we're going to find today is, what is C opt and how much can we add to a given vibration mode. So today we will only consider the problem where the damper is supposed to introduce damping to a specific vibration mode. And the damper cannot be too stiff, because then it simply locks the placement or the motion of the cable at damper position. But of course it cannot be too soft either, because then it doesn't really provide any forcing on the cable. So in between these two, we are looking for C opt. Our mathematical problem is shown in the figure. So we consider that the damper force, that is defined positive downwards, is located close to the left support by a distance A. The total length of the cable is L, whereby A prime is equal to L minus A. For this cable, we will divide it into two parts. We'll divide it into a left part with a coordinate x, and we'll divide it into a right part with a coordinate x prime that goes from right to left. So the left support is at x equal to L, and the x equal to L, and the right support is at x prime equal to 0. So we simply introduce two opposite coordinate systems to utilize the nice boundary conditions at the support in the left end for x and at the right end for x prime. We know that the partial differential equation for a cable is given here as in equation 9.1, introducing the tension force T and the mass per unit length m. U represents the vertical displacement, positive downwards, and we have only loading from the damper. That means no external loading. So we are actually doing a so-called free vibration analysis, like we did for the cables in lecture number 5, and that means we are looking for an omega n, and in particular also a vibration shape xn. Today we will not use capital X. Instead we will use un as a function of x. These two are comparable if you want to compare this lecture with that of lecture number 5. Then we have boundary conditions. And the 4 boundary conditions are as follows. So let's say BC1 says that the displacement at x equal to 0 must be equal to 0. Number 2 says that the displacement at x prime equal to 0, so this is at x equal to 0. At the other end, where x prime is equal to 0, the displacement should also be 0. Then we have 2 conditions at the damper location, relating the left part of the cable to the right part of the cable. The third equation says that for the left part, where u of a, that's the displacement at damper position when x is equal to a, should be equal to the displacement u from the right hand side, where x prime is equal to a prime. So those are the first 3 boundary conditions. they are all kinematic. The fourth boundary condition is actually shown in 9.2. Let me just make a cut around the damper force and blow it up a little bit. So we have our damper location here, and we have the forcing F that is downwards, and for a positive displacement we would have that the cable will have a kink exactly at damper location, and we'll have a tension force, the left one, and we'll have a tension force to the right. Now the tension force has a horizontal and a vertical component, and we are interested in the vertical component. So let's call this Q minus and this one Q plus. And the fourth boundary condition, BC4, simply says that if we take vertical equilibrium, says that Q minus plus Q plus should be equal to F. Let's start out with Q plus. I'm moving to the bottom of this page. So Q plus is actually equal to the tension force times the displacement, or the gradient of the displacement as function of x. Now Q minus is actually, let's just say Q plus is to the right, and at the other, to the left, we will have a tension force times the derivative with respect to x, but in this case the tension force is in the opposite direction of x, and that we can compensate for by adding a minus in front. So if I take these two representations of Q and stick them in to my boundary condition here, then I will get equation 9, sorry, not 9.1, but 9.2. So this is actually my BC4 given right here. We will use separation of variables. Now, in lecture number 5, this was done by u x of t, capital X, capital T. As you can see, the representation today is a little bit different, but un as function of x is not t, is our capital X, and this exponential function here is our capital T. And we had something similar in lecture number 5 for vibration analysis of beams. In that case, for beams, we didn't assume a general expression for capital T. We assumed a cosine representation of the temporal part, that is the T function. In this case, we do it more general than the cosine, but more specific than a general T, namely a complex exponential function. But this complex exponential function still represents harmonics by the real part. So therefore, at the end, if we want the actual response, we should simply take the real part of u of x of t. But it's only an analysis to find omega and the vibration shape u, and therefore we never need this real representation of the displacement function. And we also assume that our damper force is represented by the complex separation of variables, where we have the amplitude Fn and the temporal dependency by a corresponding complex exponential function. As you can see in 9.1, it considers a single differential equation for the entire domain, imposing the damper via Dirac's delta function. Now, that is not a convenient way to do it if you want to use separation of variables. Instead, you divide it into a cable that is to the left of the damper and a cable that is to the right of the damper. And then you impose the 4 boundary conditions that we had on the previous slide. So, to the left of the damper, we have the classical second order ordinary differential equation, and to the right, we have the same equation, but we introduce the x prime coordinate, which is in the opposite direction, but the only place it appears is in this double derivative. So we will actually have that dx is minus dx prime, but because we need the square of this, we actually get the same ordinary differential equation without a sign change in 9 form. So instead of solving one complicated second order differential equation, we're going to solve two simpler equations. And instead of having two boundary conditions, we will have four boundary conditions, or two boundary conditions and some transition conditions. We remember that the wave number is given by the natural frequency by this relation, and for our second order differential equations, we know that we get sine cosine solutions to the left with respect to x and to the right with respect to x prime. But both solutions contain the same wave number, the same eigenvalue, and we will impose boundary conditions to find the solution to this wave number, beta n. The first thing we do is to impose the two first boundary conditions, saying that the displacement is 0 both at the left end in x and at the right end in x prime. So if we substitute in x and x prime equal to 0, both sine terms would cancel, and therefore both b constants must be equal to 0. So that provides us with the two solutions given in 9.7, only having the two sine functions and the corresponding coefficients an and an prime. The third boundary condition tells us, or transition condition, tells us that the displacement at damper location should be the same whether we look at the left part and the right part. So there's simply continuity in displacement at the location of the damper. And that gives us a condition between a and a prime, but it's actually not convenient to retain either an or an prime. Instead, it is, at least in the theory for cables, convenient to find a new scaling parameter. And this scaling parameter represents the location of the displacement at damper position. And this replacement we can take directly from 9.8, because the first equilibrium or equality in 9.8 gives us that an is equal to una divided by sine beta na. And if we substitute that into the expression for containing an, then we get the expression shown here to the left in 9.9. From the second equality in 9.8, we get that an prime is given by un of a divided by sine, and then beta a prime. And if we substitute that into the bottom expression, to the right part expression for un of x, then we actually get an expression as shown here in 9.9. So suddenly we have an expression for our vibration mode. And the expression for our vibration mode is actually a combination of two expressions. If we want to plot the vibration mode to the left of the damper, we are supposed to use this expression. And if we want to plot the vibration shape of the cable to the right of the damper, we should use this expression over here. But be aware there's a common factor in both expressions, and they both depend on the same wave number, beta n. So the only thing we need now, before we could potentially plot the vibration shape by 9.9, is of course to find out what is this beta n. And for that we're going to use the fourth boundary condition, BC4. Let's have a look at the fourth boundary condition and the usage of it to actually find the transcendental equation that we want to solve to find beta n, our wave number, our eigenvalue. So the fourth boundary condition was obtained by a vertical force equilibrium between the tension forces times their inclination that should balance the vertical loading imposed by the damper. So that is shown in this expression here, and it should be valid for x equal to a and for x prime equal to a prime, whether we come from the left part of the cable or the right part of the cable. Let's just have a look at these derivatives. So let us take initially the derivative with respect to the left part of the cable. So that is du dx minus, that is a derivative with respect to x, and then we will have the expression to the left of the cable. That was un as a function of a, our single unknown scaling parameter. Then we had sine beta n x divided by sine beta n a. And everything here is a function of x, and that means we simply need to differentiate this sine function here, and that will transform into cosine. That means we get un of a, the inner argument differentiated with respect to x, and then a cosine beta n x divided by sine beta n a. Therefore, the derivative of u with respect to x minus for x equal to a gives us un of a beta n, and then 1 divided by the tangent to beta n a. That's also written as un of a beta n, the cotangent to beta n a. For the other derivative, we'll have delta u dx plus, this is du dx to the left, or to the right, for the right part, and in that case we should differentiate with x prime. But because dx is equal to d minus dx prime, then we should also change the sign when we switch the argument from x to x prime, or the variable. So we take minus du dx prime, and we substitute in the expression for u, that's un of a, then we have the sine beta n x prime, because we're on the right part of the cable, and we divide by sine beta n a prime. When we carry out the differentiation very much like in the above expression, we get minus un of a beta n, and then we get the sine beta n x prime and the sine beta n a prime. And that implies that the derivative to the right of the cable for x prime equal to a prime becomes un of a beta n, and then the cotangent of beta n a prime. Just enough space to write this one. So we have this expression for the left derivative and this one for the right derivative. Then we multiply with t and we add them according to BC4. That means that BC4 can be written as t. And then we substitute in the right derivative, and I forgot there was not enough space. Important as a minus here. So we get minus un of a beta n cotangent beta n a prime. And there's already a minus for the second term. So if we introduce the left solution, we get un of a beta n, and then we have the cotangent to beta n a, and I close the parenthesis, and this is equal to f. As you can see, t is a common factor, un of a is actually also a common factor, and beta n is as well a common factor. So I divide by those to isolate the cotangents on the left hand side. Obviously that's a matter of taste, but it's often a good idea to collect all variables containing a dimension, because thereby you get a fraction that tells you how this solution is going to be made non-dimensional. And also multiply by minus 1. So that leaves me with a cotangent, and I take the second term as the first here, so I get a, indicating that is to the left, so we have a little bit of ordering in our system. Then we have the cotangent to beta n a prime, and on the right hand side we get minus f divided by t un of a beta n. And this can be written slightly different, because we can have minus, and then I would like to maintain t and beta n. But f divided by un of a, this one here, tells me something about force over displacement. And that's related to stiffness, or at least a complex stiffness, because we don't know how the damper, what is the mathematical model for the damper, but what we will assume is that this f divided by u is given or represents some kind of function, here referred to as capital H, which is a function of frequency omega, and it represents the transfer relation for the damper. So that means that H as function of omega is defined as the damper force divided by un of a. That means that the damper force is given by H omega times un of a. Let us right now assume a viscous damper. The relation for a viscous damper is that F is equal to C times U at A over time T. If we remember that Ux of t is given as un of x times the exponential function to I omega t, that implies that U dot is equal to un I omega exponential function omega t. That means I omega un of x exponential function I omega t. So that leaves us I omega u x of t. Therefore, we can get rid of the dot by adding with I omega, like this, and that means that the damper force with its amplitude Fn is then given as I omega c un at A, and this defines, this was one too far, this one here as h omega. So for a viscous damper, the h omega is I, the imaginary unit, times the angular frequency omega, times the viscous coefficient c. That means in the frequency domain, we can set up this general transfer relation between the damper and the displacement, introducing the transfer function h. So in our transcendental equation that we have here in 9-10, we can replace the last fraction here, f over un, with a beta, leaving us a right-hand side that contains the transfer function of the damper, the wave number we're looking for, and the tension force T. Now, we want to convert everything into an expression for beta. Our problem is, or not a problem, but we have both an prime, or a prime, and a given in our transcendental equation. Now, if we want to eliminate a prime, we can write it as L minus a. That gives us a cotangent with an argument that is given by a difference between two variables. And you can look up into your preferred mathematical handbook and find this, not always well-known expression, for the cotangent or the inverse of a tangent to the difference between two values inside the argument. So if we take this cotangent and we stick that into this expression here, and do a little bit of manipulation, we can actually find an expression for our transcendental equation that looks like this one in 9-13. What we then do is that we are going to isolate this cotangent beta L. We keep that on the left-hand side, and everything else we collect on the right-hand side. And then we have an expression that is cotangent to beta NL equal to something messy on the right-hand side. Then we recognize that a cotangent is 1 divided by tangent to beta NL. So we simply take the inverse. So we take the inverse or the reciprocal of this, and that leaves us with this expression here in 9-14. The details I will leave to you. And it's always a good idea to check an expression like this, because we should find the undamped cable when h approaches 0. So let's assume that h becomes 0. So this one becomes 0, and this one becomes 0. So for h approaching 0, we will have a right-hand side that will be 0, 1 plus 0, and that is equal to 0. So tangent beta L equal to 0, that exactly gives us the solution that we found for the undamped cable, where we had full sinusoidal vibrations given by a wave number that is equal to n pi divided by L. So in principle, you should take this expression here and solve this for beta, or beta L. And if you don't want to assume that h is equal to 0, you could set h equal to I omega c. The same here, I omega c, and then you would have the solution for a viscous damper. Now that we can solve the transcendental equation quite easily for a given damper function h, let's have a look at what happens if we are not satisfied with having a fairly complex transcendental equation, but we would rather have a nice simple expression that is explicit and does not require any plotting or f-solve approach in Maple or whatever you want to use to solve this fairly complicated problem. So, the first thing we realize is that when we put a damper on the cable, the damper will impose a small change in the natural frequency because it's placed quite close to the left support of our cable. And that means the complex beta NL, we can write this conveniently as the undamped beta NL plus a change delta beta NL. And the undamped value is equal to n pi plus delta beta NL. Now when we take the tangent to this complex wave number, we've just shown that's the same thing as taking the tangent to n pi plus delta beta NL. Now the tangent is periodic in n pi. So that means this actually provides us with the same solution obtained by simply taking the tangent to the second term, that's the delta beta NL. Now for small arguments, for small delta beta L, the tangent will be approximately equal to its argument. So for small values, for d much smaller than 1, just for small values, we will have that the tangent approximates this change in wave number delta beta NL. And this delta beta is then given as the full complex beta, that's the solution to the transcendental equation, minus the solution without the damper, that's n pi divided by L. Therefore, we can approximate the left-hand side directly by delta beta n. On the right-hand side, we have a sign, and signs can be approximated by the argument for small values of a. So here we have assumed that a is much smaller than L. And that means for small a values, we have that the cosine times the sine is also approximately equal to beta NA. And if we plug this into the solution on the previous slide, we get this very compact and very neat solution to delta beta n over beta n. And remember that beta n is equal to the natural frequency multiplied by the square root, where we inside have the mass per unit length divided by the tension force. And now we kind of have to decide whether we want to do this in omega or in beta, because on the left-hand side of 918 we have beta, but on the right-hand side h is a function typically of omega, the natural frequency. And later in this lecture we're going to have a look at general damping of structures, and in that case it's very convenient to have the natural frequency omega as the solution parameter. So therefore we switch the left-hand side to omega, so that the entire expression is now a solution in the natural frequency for omega. For the beta function here, we actually had the complex beta in the denominator on the right-hand side, on the left-hand side. But let's assume that we simply add in some kind of approximate or mean value for this natural frequency in the denominator on the left-hand side. And that means we'll get a solution for the change in natural frequency, that is the complex natural frequency minus the undamped natural frequency that we refer to by a 0. So once we have the solution for delta omega n, we will actually be able to find the full complex natural frequency by this solution delta omega n when we add the undamped natural frequency. So although the expression in 919 is not formulated in terms of omega directly, but only in terms of its increment with the delta, it's quite easily afterwards to find the full complex value by simply adding the real valued natural frequency without damping that is given here in the second term of this expression. I would like to introduce the two limiting cases. The first one we already know. Let's assume that the damper is removed, or its apparent viscosity simply becomes 0. That means we have a cable without damper. So it vibrates like this, and omega n is equal to omega n0. the undamped case. However, the other case, where the damper becomes so stiff that it restrains displacement or constrains displacement here at damper location, in that case the cable will vibrate like this, but with a reduced cable length. So over here the cable length is L, and for the other case, with H approaching infinity, we will actually have a slightly higher natural frequency because we have a reduced length. So here we have omega n equal to omega n infinity. This one is larger than omega n 0. So the undamped natural frequency is given by this expression here. You can look up lecture number 5 for cables. And that means that the same solution can be used for the locked natural frequency. That's the one with infinity, but you will have a reduced cable length that is now L minus A. And you can write this omega infinity as omega 0 times L over L minus A. And this simply shows that omega n infinity would be larger than omega 0. Now, what if we use a mean value of these two limiting natural frequency as our omega n bar? And we plug that in to this expression here. Then we can actually rewrite our solution in 919 so that we get this extremely compact expression in 920. Let us have a look how we can actually utilize this omega n infinity to maybe get an even more compact expression for the complex natural frequency. So let's write the solution delta omega n over this mean value natural frequency. That was A divided by L, the relative damper location. Typically this is of the order of 2 to 5, maybe 6%, not more than that. And then we have the transfer function normalized by the cable stiffness. And we'll have divided by T. Now, first case, H equal to 0. That means that delta omega n divided by omega n bar becomes equal to 0. That means that omega n minus omega n 0, omega n bar is equal to 0, and that recovers the solution that we would like, namely that the complex natural frequency recovers the undamped natural frequency for the cable without the damper. And that is what we have over here, written in small underneath the drawing. So this is the correct solution. This was just a check. Now we want to use the other limit, where H, let's just say it approaches infinity. In that case, delta omega n divided by omega n bar becomes A divided by L. And then we have, roughly speaking, infinity 1 plus infinity. These two will cancel. Thereby we get A divided by L. That means that the delta omega n becomes equal to A divided by L times this mean value with a bar on top. This is for H approaching infinity. So this is a real value, and the delta we then approach or write with an infinity sign, and it's equal to this infinite frequency minus the undamped frequency, and that is equal to A divided by L omega n bar. So we can actually write the A divided by L as the increment between the locked frequency and the undamped frequency. That's written in terms of this delta value here, and that is given, or it must be divided by omega n bar. So the limit where H tends to infinity actually gives us an expression for the damper location in terms of the locked frequency increment delta omega n infinity. And we can substitute that into the original expression. Thereby we get the complex frequency increment divided by the mean value as the infinite increment divided by the same mean value, then we have the fraction with HA divided by T, 1 plus HA divided by T. So the two omega n bars, they cancel. We can divide by the infinite increment and get the final, very compact expression, where we, on the left-hand side, have the increment in frequency divided by its largest increment, that's the infinite increment, and that's given by the expression on the right-hand side, where the damper is introduced by this h function, but in non-dimensional form when multiplied by a and divided by t. And that is actually what is stated here in this box in 9.20, providing us a solution for the complex increment, normalized by the real valued maximum increment, and on the right-hand side we need an expression for our damper given by this h function. Let's assume that we have a viscous damper. For the viscous damper we had that h was equal to I omega c. In this case, the right-hand side, the fraction, can be written in terms of a non-dimensional damping parameter called eta. And when introducing the viscous damper and assuming that omega is approximately equal to the undamped natural frequency, then we get an eta value that is equal to omega c multiplied by a divided by t, where we on the right hand side have introduced this approximation. So the expression is as well an approximation, but it takes on a very simple form. It's I eta divided by 1 plus I eta. And this you can write in terms of its real part and its imaginary part. Let's plot the real part along the horizontal axis and the imaginary part along the vertical axis. And then we increase the values for eta. So it starts from 0, then we increase by 0.01, 0.02, all the way up towards infinity. So for 0, we will have 0 increment both in the real and the imaginary part, so we start at 0, and then we start to introduce damping and we move into the complex plane. And we step along a curve that apparently seems to be semicircular. When we initially increase eta, we also increase the imaginary part, but something happens around this place. Here we reach the maximum imaginary part, and when we increase eta beyond this, we actually approach the real valued axis and end up down here for eta approaching infinity. Now damping is associated with the imaginary part of the complex frequency. You can go back to lecture number 1 and see that the damping ratio is actually defined as the imaginary part of the natural frequency divided by the natural frequency, or the absolute value of the natural frequency. So large zeta, large damping ratio, implies a large imaginary part of the complex frequency. So at this top point, we are at our optimum. The question is, for which eta do we actually obtain this optimum? So let's make another plot. Let's plot the imaginary part of the complex frequency, not as function of its real part, but as function of the damper parameter. And we see that we increase until, yes, we exactly reach that the optimal non-dimensional damping parameter is equal to unity. And that means that the optimal viscous parameter from the expression in 9.23 is equal to T divided by A and then omega n 0. So this depends, of course, on the mode number, because omega n changes for each vibration mode. So this is summarized, the optimal calibration and the maximum damping is summarized on this slide, just indicating the solution to a complex natural frequency, and that the damping ratio is the imaginary part divided by its absolute value, and the absolute value is approximated by the undamped natural frequency. If that is the case, then we can go back to the previous slide, take the imaginary part, that's the one we have here, and divide it by omega 0, and thereby we get this expression here for the damping ratio. Now for the damping parameter eta equal to 1, then this fraction actually becomes 1 divided by 2. So for cable damping, we get an extremely neat result, namely that the attainable damping, the damping ratio that we get out of it, is half the value of the relative distance to the cable. That means if we place our damper close to the left support, where we have A to the left, and we have the entire cable length as L, the typical value will be 0.4, and from that we will get 2% critical damping. Now a typical cable, suspended cable, taut cable, will have a structural damping ratio of around 0.5%. And that means 2% is approximately 4 times the damping that is available in the structure. And that's such a factor we're often very satisfied with. The rule of thumb is, if you add a damper, make sure to at least multiply the already available damping by a factor of 2. Double up damping. The optimal viscous parameter that provides us with this optimum in attainable damping is given by the expression that we had on the previous slide, and if you substitute in the expression for omega n0, you get this value here. So you need to know your cable properties, M and T. You need to know the length of the cable and also the location of the damper, but then you can go out and buy yourself a viscous damper that operates optimally on the cable. So for 2% location of the damper, you can see that we follow the damping curve quite nicely, and we get half of L divided by A. But if we choose somewhat larger distance to the left support, then we see that our analytical solution is not really that good compared to the full solution by solving the original transcendental equation. So we kind of underestimate the damping. But underestimating is good. That means in real life we get more than we expect. Now we have had a look at damping of cables, a very particular case. The taut cable with a damper very close to its left support. We would like to extend this to a general structure, a finite element structure, where we can apply the damper wherever it is required or beneficial for the structure. Let's assume that we have some kind of building structure. And it's not limited to building structure, but this is a nice example because it has 4 degrees of freedom. And on the left figure, we have a damper acting directly on Q3. So Q3 is defined as the vector placing the damper, that's W, multiplied by the Q vector. And that means that this V transpose must be 0, 0, 1, 0 for Q1, Q2, Q3, and Q4 to isolate Q3 by this scalar product. And this defines the so-called connectivity vector W. Now on the left figure, to the right, we have that the damper operates between the 2nd floor and the 3rd floor, and that means it experiences the difference Q3 minus Q2, and if we are going to write that as the connectivity vector transposed times the full displacement vector, then we will have a minus for the 2nd entry and a plus for the 3rd entry. You can see here we ignore that the damper is actually inclined, only having unit values inside our W, but the principle is quite general. So our actual damper force, F, if it's viscous, is then given by a viscous coefficient times the the connectivity vector times the displacement of our displacement, or the time derivative of our displacement vector. If we go into the frequency domain, that means we assume harmonic motion by this complex exponential function, then F actually becomes equal to I omega C W transposed times Q. We had this for the cable, that a time derivative in the frequency domain can be written by I omega times the corresponding displacement vector. And this then defines, or can be written as H of omega times W transposed times Q, where for a viscous damper we have that H of omega is equal to the I omega C that we also had for the cable. So we can introduce our damper force as a transfer function times the connectivity vector transposed times the displacement vector. So we substitute this relation directly into our vector representation of our force, and you can see there's a minus here. That means we consider the forcing as an external load on the right hand side, and that means that we can write this damper forcing as minus the transfer function representing the temporal dependency of our damper in the frequency domain, and then we get an outer vector product. So we have the connectivity vector multiplied by its transposed. That gives us a large square matrix with a couple of unit values inside. And then we can multiply by our displacement vector. If we have multiple dampers, each of them will have its own connectivity vector, providing a summation of these outer vectorial products and multiplied with different transfer functions. That means in the frequency domain we have an equation of motion that can be written as minus omega squared, the mass matrix, plus any damping matrix, plus the stiffness matrix, and everything here is multiplied by Q, and on the right hand side we have minus the summation over K, and we have HK, W transposed, and they are also both with K indices, and times the omega. And that gives us the equation of motion that we have in 932, where for the sake of generality we have also introduced an external load. Could be wind, could be waves, depending on your structure. Now we want to do system reduction on this equation of motion, because we want to find the optimal transfer function, and of course for our viscous damper we want to find C optimal. And it's just too complicated to have 932 written in the way it is. Now we would like to go to modal analysis, as indicated in 931. The classic case is that we say, alright, we would like to design our damper to a particular vibration form. That could, for instance, be this vibration shape here, the first vibration mode for such a building structure. So we're looking at mode number 1. Could be any mode, but the illustration here is certainly for the first vibration mode. Now, modal analysis tells us that the full displacement vector is given by the undamped vibration shape times the modal coordinate. However, the presence of the damper, as indicated here by this red connection, of course has an influence on this vibration shape. So only including this undamped vibration shape would not provide us with a very accurate model. It turns out that we need a correction. We need a second vibration mode. And it's not the vibration mode for the second mode or the third mode. It's also a vibration shape for the first vibration mode. It just looks a little bit different. So let's go back to the cable. For the cable we had two limiting cases. We had the undamped vibration shape, and we had a modified vibration shape where the damper link was fully locked, and we could provide that with an infinite sign here in the upper index. So the actual vibration shape is somewhere in between these two limiting cases. If the damper is too soft, then it operates as to the left, while it becomes too stiff for a too large value of H, then it vibrates more like the left mode shape, with a slightly increased frequency because of a slightly reduced effective cable length. So what if we introduced the locked vibration mode as well for the building structure? And if the damper is placed between floor number 2 and 3, then a rigid damper link simply makes sure that the displacement Q2 is equal to the displacement Q3. And therefore we can add this additional mode shape as the vibration shape of the second term with a second modal coordinate psi infinity. We can write that in standard modal analysis form, whereby the two modal coordinates psi 0 and psi infinity are collected in the boldface psi vector, as shown over here. So for the cable we had to solve two transcendental equations to find omega 0 and omega infinity and the corresponding vibration shapes. And the same way, of course, for the finite element structure. So the undamped case is simply solved by solving the generalized eigenvalue problem without the damper. But with the damper fully locked, we get reaction forces on the right-hand side that enforce that Q2 is equal to Q3. And that gives us a change in the natural vibration mode and its corresponding frequency. So the locked natural frequency omega infinity is inherently larger than the undamped natural frequency omega 0. It is sometimes quite inconvenient to directly solve 933. Instead, it's sometimes more appropriate to introduce a slightly modified eigenvalue problem that gives us 0 on the right hand side, because from that we will get a matrix K infinity that is equal to the original structural matrix plus this additional term that I've simply introduced. So it's a fudging term that imposes what we refer to as a stiff spring. So this artificial spring stiffness is located exactly where the damper is located. So it makes this locking possible if K infinity is large enough. So this stiff spring is typically chosen to be around 1000 times the largest diagonal element in the original stiffness matrix. By that, we will not get any numerical problems, and it's typically large enough to do the restrainment of the mode shape as shown in the figure to the right. So it's much easier numerically to solve this. For instance, in MATLAB, you will simply just implement K infinity, M, push the button, and you will get both the mode shapes and the natural frequencies. And this implementation is actually also suggested in the report number 2. Let's perform our system reduction by our reduced modal representation. Now I've copied the equation of motion and written it on the top of the slide, and we're going to introduce Q equal to S times Xi. Now I do that. That means I'm going to just introduce S times Xi vector, and then I'm going to pre-multiply with S transposed. So on the right hand side I also get S transposed times F. Then I multiply from the left with transposed S and from the right with S into my brackets. And that means I'll get my modal stiffness matrix, my modal mass matrix, and I get these components here with S multiplied onto my connectivity vector. Now I'm going to normalize my mode shape U0 and U infinity so that modal mass in both cases is equal to unity. It's just to avoid too many variables inside my equation. That means the corresponding projection onto my stiffness matrices provides me with the two limiting natural frequencies omega 0 and omega infinity. The multiplication S transposed times W provides me with two terms. There's one term, that's the first one, where U0 is multiplied by the W, and that gives me some kind of amplitude, telling me what amplitude will the damper experience. Now U infinity multiplied by W will per default be equal to 0, because W identifies exactly the location on the structure where the displacements are 0, or the change in displacement is 0, so therefore this factor here will always be 0. So from 935 we have two equations with two unknowns, and these two unknowns are Xi0 and Xi infinity. That means if we actually write out this 2 by 2 matrix relation, we will find this fairly neat system of equations. And we have a parameter in the two off-diagonal terms that we've referred to as kappa, And it turns out that kappa represents the cross-coupling of the two mode shapes with respect to the mass matrix. In most cases, the U0 will be approximately equal to the U infinity. The location of the damper is often very limited, its authority is limited, or it is, as for the cable on the upper right, it is placed so close to the support that these mode shapes are as well very much alike. And if they are almost alike, then the projection onto the mass matrix should be very close to unity. And actually it's equal to unity minus this correction term. So it becomes less than unity. But for all practical purposes, we will assume that it is equal to unity. Of course, this is definitely an approximation. So for structures where the location of the damper is so strong that it can actually change omega 0 into a very different omega infinity, then this kappa will be substantially less than unity, and then what we will derive in the following will not be very accurate. So it's always a good idea to check kappa and see how close it is to unity. Now, we have this expression solution here, where we also have some external loading. But if we are going to make free vibration analysis and design our damper based on this, we will actually assume that the external loading is 0, and that means we have a characteristic equation obtained by the determinant to this matrix equal to 0. And it's a 2 by 2 matrix. That's an easy task. So this is actually done in this center equation here in 943. So collected everything that is independent of h on the left hand side and everything that is multiplied to h on the right hand side. Now for a viscous damper or any multiple damper, we have that the h function is equal to the sum of our individual h transfer functions, and it turns out to be convenient to introduce this modal amplitude squared inside the summation so that we get something that is equivalent to the single damper case that we had for the cable. If we assume viscous dampers, then for the viscous case, then hk is equal to I omega ck. So we can introduce that. The I omega can be placed outside the summation, and what is inside the summation can then be written as a common viscous parameter, given as the sum of the actual viscous parameters multiplied by the modal amplitude squared. So this uk, you remember, is equal to the number k connectivity vector multiplied by the undamped mode shape. So we can replace the summation by this representative h function to get a fairly nice solution. Now, what we're going to do is we're going to isolate omega squared minus the natural frequency omega 0 squared on the left hand side. We're going to divide by the infinite change, and on the right hand side we then get a fraction where we in the numerator have h divided by the change in frequency squared. In the denominator we have a unit value, and then we have exactly the same fraction down here, and the only change to the cable solution is that we have this modification term, but we see that this modification term is multiplied by 1 minus kappa squared, and for kappa squared equal to 1, this term will vanish, and we get a solution that looks extremely much like the cable solution that we had a while ago. Let's make some further approximations to get a solution that can be used to calibrate our dampers. First of all, we introduce omega squared minus omega 0 squared. That's equal to omega minus omega 0, omega plus omega 0. And we do the same thing for the infinity frequency. And if we go one slide back, we're supposed to divide the upper with the lower. So in that case, we simply assume roughly that these two will cancel, so that we get the fraction that we see here. And then we introduce the change in frequency relative to the undamped frequency, and we introduce the maximum change in frequency, that's delta omega infinity, given as omega infinity minus omega 0. So this one is complex and contains the natural frequency we are solving for, and this one is real valued and represents the change in frequency due to the presence of an infinitely stiff damper. On the right hand side, we can introduce a damping parameter just the same way as we did for the cable. It looks a little bit different. It contains the summation over many dampers, it contains the imaginary unit, and instead of A over L, it contains the change in natural frequency between the infinite case and the undamped case. But it turns out that we get exactly the same solution as we did for the cable. And that means we know that optimal calibration is equal to eta equal to 1. So if we introduce our eta value, rewrite it a little bit, we can end up with an expression like this. And again, we can define what is given in the numerator as an effective viscous parameter C0. So the optimal effective viscous parameter is 2 times the change in natural frequency between the two limiting cases, that's the undamped case and the infinite case, where we remember that C0 in terms of multiple dampers is given by the actual viscous parameter multiplied by the amplitude squared. Now, if we plug in eta equal to 1 in our expression, and we remember that the damping ratio is given as the imaginary part of omega 0 divided by some kind of mean value natural frequency, it turns out that the maximum damping ratio can be written in this extremely simple expression as the change in natural frequency given in the numerator divided by the 2 times a mean value, here represented by omega infinity plus omega 0. So this is the damping you get out of it if you calibrate your viscous damper according to this extremely simple expression. This definitely shows that the math is complicated. Have a look at it, be patient, but the solution is simple, at least for the approximations that we have made. The final thing I want to do is to recap the procedure. And in most cases, you're going to consider a single viscous damper on your structure, like we did for the cable, like we illustrated for the shear frame or portal frame structure on the first slide of this more general damping procedure. So, you're going to solve the undamped eigenvalue problem initially. So, that is k minus omega 0 squared mu0. This provides you natural frequencies and it provides you with the mode shapes. Then you decide which mode you actually want to damp. The illustration, at least the figure that we showed in this slide, indicated mode number 1, but the theory should be applicable for any vibration mode. What is important is that you normalize this undamped mode shape to unity. I believe in MATLAB, for instance, that is done by default, but always make sure that your U0 is normalized to unit modal mass. Then you need to determine your modal amplitude. This was the UK value that we had in the theory. Let's just omit the K index because we only have a single damper. Then you're looking for the infinite natural frequency, and that you'll find by logging the eigenvalue problem. So that means you'll find this K infinity minus omega infinity mu infinity. And remember that this K infinity was your original K plus your stiff spring multiplied by your outer product of the connectivity vectors, in this case only the single connectivity vector. So you have to solve 2 eigenvalue problems to make this analysis, and remember to establish your infinite spring stiffness matrix in this way. Now it's written here that you should also normalize the mode shape U infinity to unit modal mass, and the only reason to do that is that it's always a good idea to calculate this kappa value and check that it is close to unity. Even if it's not close to unity, I would anyway try to use the steps in 5 and 6 to actually find the optimal viscous parameter and the maximum damping ratio. Because what is typically the case is that although your theory is not really accurate, we will, as indicated here for the cable, be conservative in our estimate. So you will most likely get more damping out of it than the theory predicts. So my advice, my recommendation is that if kappa is actually significantly smaller than 1, use steps 5 and 6 anyway. If you want a more accurate solution, you should actually attend this equation 945, introduce your viscous parameter into H. You should not eliminate this intermediate term, and solve this equation iteratively or numerically, and find optimum H by trial and error. However, for the case when kappa is engineering-wise close to unity, it's actually kappa squared that should be close to unity, then we know that the optimal calibration is eta equal to 1. That provides us with an expression for C, and remember that C0 in the slide was C times U squared, and that means that C optimal is equal to C0 optimum 1 divided by U squared, and that is actually the expression that we have given here in 5. Extremely simple. Calculate omega infinity, omega 0, take the difference between them, find your U parameter, take the divide those two and multiply by 2, and go out and buy yourself a viscous damper from a manufacturer. What you would get out of it is given by just a simple expression, because you should take the change in natural frequency and then you should divide by the summation of these two limiting natural frequencies. And if you say that this limit is approximately equal to 2 times the undamped natural frequency, then you'll get an expression that is just as simple as for the optimal viscous parameter. So these two expressions are those you can use to calibrate your viscous damper on a general flexible structure. Could be a cable, could be a bridge, could be a high-rise building, could be a part of an engine, could be an offshore wind turbine. The theory is for a general finite element equation of motion. As an example, let's consider an extremely flexible structure. It's a 10-story shear frame or portal frame structure. I've drawn it here in the bottom right. So we are going to consider 3 cases. We're going to consider the case where the damper is located between ground and the first floor. We will have the case where it is placed between the 3rd and the 4th floor, and 4, 5, 6, 7. And third case where it's placed between the 7th and the 8th floor. So 3 different cases. They are not placed on the structure simultaneously in this case. So if I were to ask you for the first vibration mode that we're going to damp, which of these 3 configurations would be the most effective? You should remember that the mode shape for a shear frame structure has its largest curvature at the bottom, and then it becomes almost vertical for the upper stories, a little bit exaggerated in this drawing. And that means the stretching is much larger for the bottom floor than for floor number between 7 and 8. And that is immediately seen in the displacement vector, indicated by the amplitude. And remember that UK is equal to the connectivity vector for our configuration times the undamped vibration shape, and U0 is indicated here by green in the right bottom figure. So for the bottom location we have a fairly large value, whereas between stories 7 and 8 we have a reduction of approximately a factor of 2. So for the 7 to 8 location, we will have a fairly small half-circular locus trajectory in the complex plane, while for the bottom location, we'll have a very large half-circle. And again, maximum damping is represented by the largest imaginary part of our natural frequency, or the change in natural frequency, and it is much larger for the 0,1 location than it is for the 7,8 location. And that is also seen when we multiply our eta 1 value. For the 7,8 location, we have the maximum exactly at eta equal to 1. And of course, it's also equal to 1 for the 0 to 1 location, but again, we have a much larger imaginary part, actually damping ratio, compared to the upper location. So the design of a damper system and its location are both initiated by looking at this modal amplitude for our different damper locations. And you can also have a look at the change in natural frequency. That's actually the diameter in these half circles. So for 0 to 1, let's just start out again. This is the change in natural frequency when we are between 7 and 8, whereas this one is the change in natural frequency when we are between 0 and 1. And this one is much larger than the 7,8 version. So we get much more damping by placing the damper between the two bottom floors than we obtain by placing it between the floors 7 and 8. And there's actually a factor of 3 between them, and that is approximately also what we see here. So there's roughly a factor of 3 between the imaginary parts of the natural frequency for these two locations. So the lower placement is the most effective. So place your damper, if possible, where the stretching of the damper is largest, and that is given by a large value of both this U value, but also the delta omega infinity. The problem is, of course, to find delta omega infinity, you actually need to solve the second eigenvalue problem. To find this UK amplitude in the upper row of the table, you only need to solve the undamped natural frequency. And typically you've done that already during the design of your structure. You can actually consider the placement and sizing of multiple dampers. The theory is, like the rest of this lecture, fairly complicated, but again, the result is extremely simple, published in recent papers, and you can have a look at this if you like. It will not be part of the oral exam unless you decide yourself to actually introduce it. So what we will consider for the oral exam is the general theory for either a taut cable or for a local damper placed on a general structure. We will most likely provide you with the chance to decide to either consider one topic or the other. Of course, if you are so lucky to draw the lecture number 9 as topic for the oral exam. That was actually everything I scheduled for today. Fairly lengthy lecture, and next time we will then have a look at another type of damper, the so-called tuned mass damper. It works in a different way. It's a resonant device that is extremely effective, but only with respect to a single vibration mode. Enjoy!